So real quick, just a quick show of hands. How many people in this room have been hands-on with a cloud? Any type of cloud? Any type of cloud that you have? All right, perfect. Excellent. So we got a bunch here. So as Chad said, my name is Vince Puglia, and I'm a developer advocate for Dialogic. And for the better part of a year, Dialogic's been working on getting our media server into the cloud. And for the past 6 months, we've been really focused on seeing how fast this car can go. So seeing how fast our media server and how much it could scale in the cloud. So for the better part of 6 months, this has been our focus in the cloud. This presentation, this 30 minutes that I have is a quick summary of what we've been doing and what we've been experiencing. So this is everything from perhaps the completely obvious to maybe some head scratchers. So for the next 30 minutes, I want to kind of share with you our experiences there. I know I have probably about 2 minutes before you guys start checking email, so I wanted to give you the short version here. If you start looking at the ceiling, if you look at the ceiling of the cloud and you start looking at how fast this thing can go, and you can compare it to comparable servers and comparable what's out there, dedicated servers, the performance at the top level is exactly the same. So if that's the takeaway today, that's what you have. So if you want to check email after this, that's fine. But if you want to, so the why now. So here, the why of the media servers hasn't changed all that much. And it's been the why for a long time now. The why, the need for a media server has been pretty much the same. And I call these the big four. And these it goes beyond this, but the big four primarily for a media server are recording, playback, transcoding, so under transcoding as well as transrating, transizing, and also the multi-party conference, broadcasting the talking heads and such like that. But what is changing, what has been evolving, is the where, and where this has been evolving. And these are I'll call it the four waves, and I could certainly see an argument for other waves in here, but these are the four waves that are typically where media is being processed and has been processed. So first, and I call this the pre-virtualization world, and this is where the media has been processed on a purpose-built board. So it's a specific hardware chip on the board, on the actual hardware device doing it. It is purpose-built, like I said, and typically it is highly reliable. I know I have customers out there using a 4-port analog card from the 1990s on Windows 95. So this stuff, for the most part, is pretty reliable. The cons of that, though, is that it has limited scale. So if you buy a 4-port analog card, you get 4 ports. It also is slow to deploy. If you are looking to go to 8 ports, you have to obviously open up and give another ports. The next wave is the host-based processing, and this is basically where they took the DSP processing from hardware and moved it onto the host, so typically using the hardware chipset of the host. And this was great. This was moving in the right direction. So the pros of that is that it's hardware agnostic, so you could typically get a little bit more out of a hardware. Getting more out of the hardware and not depend on what it is. It also increased the scalability, so no longer are you bound by a hardware set. You're bound by typically a license and typically how much the processing power can do. The downside of that is typically it's a single tenant per host. So we're not into that multi-tenant capacity yet. So typically in the host perspective, you have to, it's a single host. The next wave got into the virtualization. And basically the virtualization introduced the multi-tenancies. And basically the multi-tenancies is being able to reduce the total cost of ownership by being able to have multi-tenants on a host. So now you can start having application compartmentalized. You can have it be individual applications run, multiple applications run on a single hypervisor. And typically that meant you had faster provisioning as well. So no longer did you have to wait for provisioning to happen. You can spin up, spin down pretty easily. The cons of that, though, and maybe this is a fallacy of some people, it still needs to share. There's still one sandbox that you need to share under the hood. So if you're trying to get more out of a virtualized server by putting more onto it, it's impossible, right? The underlying hardware is what it is. And then along with that, it's the same or less scalability. So you're not getting much more scalability out of that. One would argue that a tangent of this is the container era, and I would probably agree with that, but the container era is probably another conversation for another day, so we'll kind of acknowledge it but move on past it. Then we get into the cloud, and that's the primary discussion today is the cloud, and this is the cloud-based virtualization era. And the pros typically are that it's endless global scalability. So you no longer are bound by a single tenant. You now have the scalability of the cloud, which is typically global. It also is very cost effective. So you just pay for what you use, you pay for the minutes you use, you pay for the compute you use, and that's it. So there's really no commitment on what you do. Along with that, just like in the past, the increased speed and agility is with the cloud. Now, where the cons come in, that's what we're trying to explore. That's what the unknown is. So what we're trying to do is understand what the cloud can do and how fast it can go. So with that, there are a lot to choose from. It seems like the going thing is to spin up a cloud these days. So if there are a lot to choose from, and there are a lot of options. So anywhere from Rackspace, Amazon, the Google Cloud, Microsoft Azure, and so we had to pick one, and we had to focus on one for what we wanted to do for our testing. So the testing that we did, we focused on Amazon, and the reason why we focused on Amazon was, one, we get this request larger by far more than anybody else. So the most requests come in from Microsoft. From Amazon. One of the stats that I had read was if you bundle up all the compute, if you bundle up all the cloud that's out there, 90% of that belongs to Amazon. The next 5% belong to Microsoft, and then the rest are that last 5%. So larger by far, Amazon's doing the most in this space and owns the most market space for this. If you're not familiar with Amazon, if you're not familiar with the Amazon cloud, what they call their compute cloud is called EC2, so Elastic Compute Cloud. Basically, it's comprised of, I think, 12 or 13 regions spread throughout the world. Then from there, and within each region, they have multiple sub-regions, which they call availability zones, that you can then deploy your services into. So basically what they do is they give you a front end to being able to spin up services, spin up instances in the cloud. And that's why I like this. So maybe a question that you guys are thinking is, well, why is a developer advocate talking about infrastructure? Well, in my eyes, moving to the cloud takes infrastructure and moves it more towards code. It allows me to use APIs, a web UI, to now start spinning up instances that I need for my cloud. And with that kind of brings me to my first lesson. So I do a lot with developers. And what Amazon does is it gives you EC2 instances to pick from. And it gives you anything from a T2, which is specific for web servers, all the way down to the graphics, the G2s, the video encoding, the D2, which is specific for file servers. But most of my customers, most of my developers that I talk to are deploying, if they're using a cloud, they're deploying on either a T2, an M4, or an M3. So if you can imagine me coming in as a media server, which do you think they want to deploy a media server on? Most likely the smallest one, the T2, the M4, the M3. But media processing is such a heavy intensive, compute intensive process that really it's made for more of the C4, the C3 class. So really the first one, this is probably the most obvious of the lessons learned, is make sure you're picking the right one. So when you're using something that is compute intensive, such as a media server, use the right class of instance. Now when you start looking under the hood and you start looking at what it actually comes of these instances, and as I said, we're focusing on the C4 instance family. If you start looking under the hood and see what it is under there, it's made up of an Intel Xeon E5 Haswell series. And this is specially made for Amazon, so this is OEM for Amazon. And it's typically, it is built, the host under the covers is 40 virtual CPUs and capable of, and it also has 75 gig of memory. But what they do now is the sharing is they start to provision that down. So you have complete access to be able to spin up any instance you want, going from large to small. So in this case, they have a C4X large, which is 36 CPU, and 60 gig of memory, all the way down to a C4 large, going from 2 CPU and 3.75 gig of memory. So you have the choice for when you spin up an instance, you can choose any of these. For our conversation and for what we did, the cost, as you can imagine, goes up as you choose the instance. So for our testing, we wanted to bookend this. So we wanted to choose both ends of it. We wanted to pick the ceiling as well as the floor. So what we did was we chose to focus our testing on the C4 extra large and then the C4 8XL. We also needed a control. So what we needed was a hardware server that was very comparable to what Amazon was putting out. And so what we did was we bought a C4 replica. It wasn't, as I said, the E52666 is not available for sale. So what we bought was the next model down. So we bought a replica of it. Which brings me to the next lesson learned. Clouds are expensive. And Alan's laughing because he knows this. But if you take a look at it, and I know this, there are more variables in there, right? There is the data transfer. There's the cost to maintain the server. There's other things. But if you start to boil down the numbers, and you start to compare the ceilings, right? So we'll focus on the ceilings for now. If you compare the ceiling of Amazon, which costs you $675 per hour versus how much it costs for us to buy the hardware, which is about $5,000. You start to break that down, and you're really not getting that much out of a return on investment. You're really looking at about 124 days of being able to run that server, which a media server you typically want to run quite a bit. But now, that's the ceiling, right? So now what we want to do is start getting into what else can we do. And Dialogic is a very, how do I put it? We're a very test-conscious company, so we do a lot of testing. So what we do, though, is want to make sure that the cloud is not only able to handle media, but also handle media for real-time communications. So we had 82 unique tests, and they spanned from the simple functional testing all the way up to longevity testing. So real quick, just to go through it, the functional testing, play, records, conferences, record conferences, coach and pupil. So we have a lot of instances where you're going into a contact center, join, DTMF, collections, pre and post conferencing. I'm sorry, pre and post speech. So that is those, when you're sitting at your dinner table and somebody calls you and wants you to buy something, you say hello, it connects you. That's the pre and post connection. Also, what we want to do is we want to make sure that the media control APIs we're getting through. So we have a variety of APIs. We support REST, MSML, VXML, JSR 309. So we needed to make sure that that was up. The call control, the busy hour completion, the benchmarking, so being able to see, like I said, how fast this car can go. The pesky testing, so making sure that the quality coming out of there is unaffected. And then also the longevity testing, so making sure that this media server can last hours, days, weeks, months at a time. So the longevity testing was important. And I already gave away the secret. I already said that in the very beginning, in the first 2 minutes I had your attention, was that at the ceiling, this really is something that it's exactly the same. So the dedicated server and the ceiling of a cloud is pretty much the same. But not everybody lives at the ceiling, right? We want to know what happens at the floor. And that's where things get exciting. So our expectations from what we knew or what we had learned in the past was that we were hoping for linear scale. So if we're using I think it was an 8XL at 36 CPU, you boil it down to the smaller version, the C4 XL, which is 1/9 the size. So we were hoping for 1/9 scale. But our fear was that it was oversubscribed, that the host, you put more instances on there, you get more subscribers on there, it's going to be oversubscribed. So the more subscribers, the less time the scheduler has to give us time, the less reliable service we're going to be able to give. Additionally, we're worried about the chatty neighbor, so too much output going out and drowning our RTP streams. So if I were to visualize this is what it would look like to me. So essentially, the host is just being bombarded with the VMs on top of it. But as the top of the left says, expectations don't always meet reality. So what had happened was we were seeing more performance out of the floor, more performance, and specifically 15% more performance. So what we were seeing was at the floor, we were getting 15% over linear scale, which is great. This is fantastic. So I don't yet know how this is happening, but my assumption is that Amazon wants to make sure that your service is running good even at the floor. So what they're giving you is more. They're over-provisioning you at the floor, which is great. Then you start getting into the oddities, the unidentified anomalies. And we had a few of them, and I don't want to misrepresent what had happened over the testing, but I want to at least kind of give you an idea. So I'll share two with you. So in the one case, so what we do is Amazon has a firewall. We typically open up the firewall for RTP ports. In one of those cases, and this is 3 times out of 3 months, 3 times out of 6 months, one of those RTP ports was frozen by Amazon. Okay, so if you don't know what happened, you don't have any control over their firewall. You have to pretty much just spin down and spin back up. The second was a little bit odd. We were running a longevity testing, and all of a sudden, right in the middle of the testing, the results started going down. It failed everything. And what we were seeing there was an over provision. So Amazon would over provision the service, and all of a sudden all of our tests would go away. I guess the point of this is that you have to expect the unexpected, right? You don't have control. You have to give up control when you go to the cloud. So what you're doing here is you have to expect those things. You have to know that sometimes maybe a port is going to get stuck and you have no control over that. Sometimes things are just going to go to hell and you have to spin down. You have to be prepared for that stuff. So expect the unexpected is lesson number 4. Up to this point, we've been talking about vertical scaling. Everything that stacking CPU, stacking memory on top of one instance, and being able to get more out of that instance by vertical scaling. But what's nice about the cloud is that things can be horizontally scaled, right? So this is a similar type of diagram from that they provide on Amazon. So it's basically being able to string multiple instances together to get more out of it. So the horizontal scaling, so being able to scale left and right is where the cloud really comes in. But the question is, what services can Amazon or other cloud services provide to make that easier? Backing up. So this is that nice block diagram that they give you. But if you live in the real world, this is something that it really looks like. And I'm sure probably everybody's familiar with this. It comes in spikes. It comes in peaks and valleys, right? So it's not everything fits in that nice block. So this is actually from one of my test clouds, and you can see there's spikes going on, right? But if you were trying to predict that scale and put that nice even diagram around that, it's tough to do. So in those areas where in the areas where you over-provisioned, you're essentially wasting money, right? You've essentially gone out and over-provisioned it and losing money there. Those spikes where you haven't done it properly, that's where customers get pissed. That's where they lose service, where they don't get media. That's where things get mad. So you're towing the line of being able to be delicate, but also want to save money at the same time. So with that, back to the Amazon story. So Amazon does provide a nice little auto-scaling, they call it. So auto-scaling is basically their way of scaling up and scaling in media EC2 instances so that you don't have to. And basically they rely on 2 things. They rely on the service called CloudWatch, and they rely on a service called Elastic Load Balancing to accomplish this. There's more, but these are the 2 primaries for that. CloudWatch is a service that monitors EC2 and will spin up, spin down based on CPU, network in, disk writes, failure checks, etc. But is that enough for real-time communications is the question. And really it's not. So what we were finding is that things like a stuck port or even like provisioning depends on sessions. So you need to really look beyond that. So CPU is generally a pretty good gauge of what's going on, but it doesn't give you the full story. Secondly, this elastic load balancer, it's good, right? It's good for stateless communications. But as we know, media processing is a stateful processing. So it needs to actually look into it and actually see what's going on. So the example I have here is spinning up a conference, right? The elastic load balancer won't look under the hood in order for you to know that Alice and Bob need to be on the same media server. And there's ways around that, but typically that's kind of what you want the load balancer to do. So I guess I'll finish with this. The lesson learned for number 5 is just make sure you use the right tool for the job. Real-time communications is not the same as stateless communications, right? You have to look into it and make sure you're doing real-time communications for the right job. And with that, I will summarize this, that as I said in the very beginning, the cloud does equal, at the very top of the ceiling, the cloud does equal dedicated server. So at a performance level, that does happen. The cloud era is upon us, so evolve or die, right? And then the lessons learned. Pick the right instance, beware of the costs, sometimes reality outperforms expectations, expect the unexpected, and then pick the right tool for the job. And with that, I will open it up to any questions.
Any questions for Vince?
Have you explored using GPU instances for any of your video processing tasks?
We are looking into that, and it does help. Nothing in the cloud yet. We're not yet looking into the cloud for that, but we are looking as dedicated services to offload GPU, and it does help.
I have another one. Oh,
Go ahead.
Are you looking to it more for GPU-driven like compositing and processing, or are you looking at it more as like an H.264 decode encode offload?
So large and by far the biggest CPU consumer is encoding. So what we're looking to do is being able to stretch encoding by offloading that to the GPU. So it's typically about a 4-to-1 scale. So if encoding to decoding, it's about a 4x consumption. And what we're looking to do is being able to take the GPU, offload some of that, and get more scale out of it.
Other questions?
First of all, thanks a lot for this talk. My personal experience when trying to deploy scalable media servers on AWS is that the real bottleneck in the end becomes the network. So it's not necessarily the fact that you are running out of CPU cycles, but more often than not, the issue is that you have no bandwidth available, because the bandwidth that Amazon is offering you is just intra-cloud bandwidth, and you need extra cloud bandwidth. So with many users, the real unavoidable bottleneck is the network, from my perspective and my experience. I would like to know whether or not you're sharing this view.
Yeah, so we definitely we are able to get more capacity out of the CPU. So speaking to a CPU, we are able to get more out of that. But you're right, though. The bottleneck and where it comes down to, the throttling comes from the networking. And so that's why when I was pointing out the CloudWatch and those things that are being able to scale in and out don't really give a good representation of what you can for scaling, right? So the KPIs, such KPIs that we look at are the RTCP stream and more of like a MOS type scoring. So seeing how the network's reacting, if we're getting throttled, if things are happening, and then being able to offload that somewhere else. So yeah, we do certainly see that as being one of the typical cases of throttle.
Excuse me?
Yeah.
So what's the algorithm that you use for the elastic load balancing that you explained?
What else? Sorry, say again?
What's the algorithm you use for the elastic load balancing?
So the elastic load balancer that we had used was primarily focused on the network in and out, and also the CPU consumption. So CPU is typically a pretty good gauge of what's going on in the system, but also you need more than that, right? As I just had mentioned, the CPU and the network end is not, from the CloudWatch perspective, is not a typical gauge of that.
Thanks. Did you look into scaling horizontally in multiple regions, and specifically in how latency between the regions would affect the performance?
Yeah, so primarily for this, we've stuck within region and typically within the availability zone. We are looking now to be able to start scale that across multiple availability zones, multiple regions. One of the products, and I don't want to turn this into a commercial, but one of the products that we release is called an MRB, a media resource broker. So it's basically an intelligent load balancer for media planes. And so what we're looking to do now is being able to put that in Amazon to be able to scale this, not only within the availability zones, but within the region, but also multiple regions as well. So in process, work in progress.
But no experiences from it so far?
Nothing yet, no, nothing yet.
Other questions?
I'll save that for next year. That way you can invite me back.
Is the technology here to have a huge, large-scale broadcasting services, for example, up to 100,000 people who communicate at once without any problems at all?
Right. So our focus is real-time communications. So there's a distinction between near real-time and real-time communications. So what you're speaking about broadcasting is near real-time. So adding a bit of latency, but being able to broadcast to thousands, like a Wowza or other type of service like that. We can do broadcasting, but not to the extent that we're more of real-time communication. So we can do several hundred but the broadcasting, the near real time, is capable of doing the thousands, hundreds of thousands. So our focus is the real time communications.
Any other? We have time for, I think, one more.
Yeah. So besides giving up some control when you go into the cloud, you also give up a certain kind of visibility as to help you troubleshoot, I believe. Mm-hmm. So I just would wonder, what kind of monitoring are you able to do in the cloud? What kind of Wireshark, for example? What kind of analysis can you do once you have given up that control to the cloud?
Yeah, so you do get access to Wireshark and other types of troubleshooting services that we go to the cloud. So you do have an SSH ability to get into there. So you can run Wireshark, you can run other performance type tools to use that. Where basically the control gives up is kind of being able to see what happens after it gets out of the instance. So being able to go through the firewall, for instance. We ran into a lot of cases where the firewall, or what's being co-hosted with us, so the multi-tenancy. So that's where you give up the control of who you're sharing the host with and also what's going on with the firewall.
Well, thanks, Vince.
Yep.